means what? Why is not being as hot going to make the pressure decrease?
Some of your gases turn into liquid, and there's more space for it to run around and not fly.
Okay, because some gas is liquid, so we decrease the number of gas molecules inside here. So that increases, so she said it increases some of the space for the gases that are left. What about what's causing the decrease in pressure? What do we know about pressure?
It's getting colder.
So yeah, it's colder, but what causes pressure inside of a container? Push what? Push where? So if I say I have a decrease in pressure, what do I have a decrease in, Michael? About these walls of the container. So what's happening against the walls of the container? What should I draw in my picture?
It's crushing. Pushing more out.
Smaller arrows or less collision, fewer collisions against the walls of the container. So it increases space and what? Fewer collisions with wall. Okay, and then what about this step right here? Pressure outside the tanker. What's happening with the pressure outside the tanker?
Still the same, so it's greater.
Okay, so you're saying the pressure outside, so I'm going to write that here. Pressure outside changes? Okay, so what happens to the pressure outside? So it stays the same, but now it's more, okay, so that's, you're saying it's not actually increasing, it's staying the same, but it's compared to the inside, it's more. Okay, pressure outside stays the same. But is now bigger than the pressure inside. Okay, and then what's the last thing we should say here? Why does the tanker then crush? Javier, what do you think? So if we now know that the pressure outside stays the same but is now bigger than the pressure inside, why does it now crush?
Because the temperature inside is different than the temperature outside.
Okay, so yeah, that's kind of the why, but then what can I say here? If I have a pressure outside that's bigger than the pressure inside, what's going to happen?
Puts the pressure on the tanker.
Okay, and so then what's our last step here?
It inflows.
And what's the reason? It's kind of connected to this, right? So why does it implode?
Because the pressure inside decreases and the pressure outside increases.
Okay, so the tanker, the temperature out, the pressure outside does what?
Huh?
The pressure outside does what?
Huh?
So you said the pressure outside increases. Does the pressure outside increase?
Wait, what? I'm lost now. What?
Okay, so we're at this step. We have pressure outside. We here said pressure outside stays the same, but is now bigger than the pressure inside. So what happens?
Huh? So it crushes.
So it crushes. So the tanker crushes. I guess maybe my question isn't very clear, but what I'm asking is, how could you relate this statement to why the tanker crushes? I just want one more step here. So who cares if the pressure is outside is the same, but the one inside is smaller? What does that do?
It wants to get equal.
Okay, so what happens?
So the tanker crushes.
So tanker crushes.
It tries to get in, so it puts pressure on the
Tanker crushes because why?
Pressures are unequal.
Okay, because pressures,
You caught me at the wrong time, Sean.
sorry, pressures are unequal.
I was biased.
Okay, and so then the tanker crushes, and what's the final result of pressure?
Very equal.
Okay, so then tanker crushes because pressures are unequal, and then how should I write the final result?
No more tanker.
In conclusion,
So what's our conclusion? What's the final thing here?
Pressure is so finely equalized.
Okay. When tanker is crushed. So let's look at our explanation we created here. We told the story of why this tanker crushed. Think back to before. when you first tried to explain this? What kinds of things, what kinds of ideas have changed? What have you learned, or maybe what's different from how you first tried to explain it?
Before we thought the outside pressure increased.
Okay, so before maybe you thought the outside pressure increased. What else maybe did you think before that you know that your thoughts changed? Yeah.
It was magic.
So before you just kind of thought it was magic, and so what do you now know?
That it's not magic.
And what
Science.
is it? And what about science is it?
That it's all about nature.
It's about what?
Nature.
Okay, tell me more about that nature.
That there's air everywhere, and yeah, it's about pressure.
Okay, so that there's air everywhere and it's about pressure. What else? What other new things have you learned, Michael? I need you to wake up, please. What other new things have you learned? Yeah. Let's see if I can find one here.
Michael is gone right now.
I look at a lot of these. I can find them over here. Almost none of you put anything about air outside the tanker before. So I think that one big thing that we've learned is that there is air everywhere. And you did have the air foot. But so based on what you thought before about air foot versus what you now know about air, how has your thinking changed about that? Like, what's different between your initial idea of air foot versus how we described it here?
Well, we know it's not foot.
Okay. And what else is different about it?
We know that the pressure didn't increase outside. It just kind of took over.
Okay. Good. And so, in your journals, well, first let's talk about this. We kind of have this explanation now of the tanker, and you have done some investigations of the behavior of gases. So I want us to come up with, we've talked about at least 4 different kinds of things that affect how gases behave. So let's brainstorm those. What are 4 different things that we've kind of looked at that affect how the steam or the air or gas behaves? So we have temperature. Temperature. What else? What? Okay, and what do we mean by space? And what's another way to say that in like a science term?
Volume.
Yep. Space or volume. So you looked at how volume affects the behavior of gases. What else did we look at? Somebody in this section here. What affects behavior of gases?
In some way that affects the behavior.
The phase, okay. So the gas is a phase, but you're right. If we, so gas is the phase of matter, but if a gas becomes a liquid, like here you told me, we had some gas and now it became a liquid. What did that do to what was inside the tanker?
Pressure.
Okay, so it changed the pressure. So that's one thing that we know about how gases affects how gases behave, is what their pressure is.
The amount of
Gas molecules.
Okay, and the amount of gas molecules. Good. So we have these 4 things that we've seen affect the behavior of gases. And over a lot of time, chemists have also been investigating these relationships. And we're going to continue looking at these a little bit more mathematically, because you've already seen a lot of these relationships. You know, and could probably tell me some of the ways that these affect gases and how they're related to each other. So we, over the next couple days, are going to look more specifically at how they're related. So in your journal, open up to your next blank notes section, that there's these 4 variables that affect how gases behave. There's pressure, there's volume, there's N, which is the number of molecules. Yep, write it down, please. You're going to need a whole page for this. And then there's T, which is the temperature of gases. Here, let me zoom out and show you what my page looks like. So we're going to add to this here. We're going to look at some of the relationships more specifically.
What does R stand for?
R is one that is not one of the variables. It's just a constant that makes this equation up here work. And we can look at it more carefully once we understand these relationships that we'll talk about. But R is not one of the variables. It's a constant, a number that we would always plug into that equation if we were using it. So this equation here is can be used to describe the behavior of gases. But before we kind of use all of these variables together, we're going to first look at some of the relationships between these variables. So we have pressure, we have volume, the number of molecules, and the temperature. So today we'll look at pressure and volume, and then after we're done, we'll add some things in this column to describe the relationship between pressure and volume. So here's how it'll work. We'll have to divide the class into two, so maybe 2 groups will work together and 3 groups will work together. And you'll get a syringe with a cap on it and a scale. And you're going to start with the syringe out at 50 milliliters. So you're going to figure out, you're going to line it up with 50. And then you're going to push down on a scale. So you'll push it down, let's say this is the scale. And you'll push it down at 50 and read how much weight is on the scale. Then the person who's pushing will push it down to 40, 30, 20, 15, and 10.
Ooh.
And so you'll need probably 3 different people, like 1 person to push, 1 person to read the volume or the weight on the scale, and 1 person to read the volume on the syringe. And you're going to record the weights here. Yeah?
So we're starting at 50 milliliters, but seeing how far we can push down
Yes.
on it.
So what's going to happen to the pressure as I decrease the volume? What do you expect is going to happen?
More pressure.
Okay. So we're going to see if you see that today with the weight. Remember, pressure is going to be pounds per square inch is how we're going to measure it. So you're going to multiply the weight that you get times your, well, here's your area. It's pi r squared. I just took the radius of the syringe here, and I calculated the area for you. And then the last thing you have to do is to convert it, because we talked about on the last time we met, that there's actually 14, like if I just put the scale out here, there's 14 pounds per square inch just on that scale. So we're gonna add 14 to this to do our total pressure. The air pressure plus the pressure we're putting on the scale. So I'm gonna make a graph, and there's questions to help you think about this mathematical relationship between pressure and volume
14.7 pounds?
per square inch.
How?
Just how does air put pressure? Yeah, exactly. So how does air put pressure on this?
I don't know. Gravity?
And
That's
what
why we're
else?
stuck to the ground.
Okay, but what do we know about what causes pressure too?
Air.
Air doing what?
Pushing on us.
Okay, so this air that's pushing around us that has all these collisions with us and with the scale and with the table, all those collisions are 14.7 pounds per square inch if we could measure them.
Oh,
More volume.
Equals less pressure and less collection. And then the opposite is where.
Okay, so if you have less volume, you get more pressure, which is because you have.
Wait, no, which is more pressure slash collision.
Okay, so if there's more pressure, there's also more collisions.
Yeah, because that's what you were kind of saying.
Okay, so if you could do you think that you could ever get it down to 0?
I mean, with like a car on top of it or something.
You think maybe you could? It could get all the way down to 0
I don't
volume?
know, maybe not.
Why not?
Oh, because, no, it can't.
Why?
Because there's the molecules of air, they have to go somewhere. And so they'd still be taking up space.
So if we look at your graph here, do you think this would ever go down to, like how far do you think it could get if we could extend it out?
Well, I would say here, which is like,
Yeah.
I don't know, 10.